Hello, everyone. So today's schedule is basically we're going to start with the natural language processing section 2, the second part, and we're going to have an introduction to computer vision, both the first part and the second part. And the last part will be coding for machine learning, which is actually quite important because you're going to get familiar with concepts like Hugging Face that you actually need to use for your models and the deliveries of this Olympiad. So let's start with the natural language processing part. So last time we discussed two types of NLP tasks. Actually what we're going to see is encoder-decoder models, the transformer architecture, and pre-training and fine-tuning. So let's do a throwback to last week, where we discussed two types of NLP tasks, the sequence classification task and the sequence labeling task. For the sequence classification task, Yova gave this example of sentiment analysis, this movie sucks, where we want to predict if the sentiment is positive or negative. And for the sequence labeling task, we had this example of part of speech tagging task, where we have a sentence and we want to predict the tag for the words. Now we're going to focus on sequence-to-sequence tasks. And a very classical example of these tasks is machine translation. And assume when people ask you English or Spanish, you will use machine translation to translate the sentence to Spanish. And this, the English is called source language, and the Spanish, which we want to predict, is the target language. And last time, and I mean, you all have used Google Translate. It's a classical sequence-to-sequence modeling task. But last time we actually saw in details how this works. We introduced the encoder, which gives us a good input representation in the form of contextualized word embeddings. And we also see what is a language model, which can generate text predicting one word at a time. And in sequence-to-sequence tasks, we have a string of words as input, which we'll represent using an encoder, and a string of words as output, which we will represent using a language model. But how do we connect those two? How do we connect the encoder to this language model to predict what we want? As a reminder, how language modeling works is that we take the contextualized word embedding for the last token in the sequence so far, and we compute the dot product between this vector and an embedding matrix where each word in the vocabulary is represented by a vector of its own. And in this way, often a probability distribution over all tokens in the vocabulary is calculated, where a higher dot product indicates a better match for the given word in the present context. And formally, we are looking to compute the word once, which means 11. And the probability of this word conditioned on all the past text. In this case, 3 más 8 son. And when we're solving a sequence-to-sequence task, what we really want is for the prediction of the next token in the sequence to be informed not just by the context in the target sequence, which in this case is 3 más 8 son, but also by the context in the source language. We want to compute the probability for the word once, conditioned on both the English and the Spanish text. And because the encoder encodes the source language into this abstract vector representation, and the language model maps these back to the target language text, we actually refer to the language model as a decoder when it is used in this way. So the encoder reads the source sequence and transforms it into context-aware representation, and the decoder generates the target sequence, producing one word at a time, while using the context provided by the encoder to ensure the translation is accurate and grammatically correct. And now we want to find a way to send this information from the representations of the input words to the output embedding E. But do we really need information from all words in this sequence to predict the next word in the target text, which is the word once? Not really. Like, the most important part in the source text that we should be paying attention to is the word 11, because all words that preceded have been translated already. So not all words are important. We don't need to pay attention to all the words. We only pay attention to the word 11 to predict the word once. And this is actually the attention mechanism. And it's a technical term in NLP, which is described as the mechanism of determining the weight or the importance assigned to each word when generating its output word. And attention at its core is based on vector similarity, computed as a dot product. And the similarity between the contextualized word embedding of the first word in the input and the output embedding E will directly determine how much the input of E should be conditioned on the first word in the input. And likewise, the similarity between the contextualized word embedding of the last word in the input and the output embedding E will directly determine how much the output of E should be conditioned in this last word. And the attention weights are used to compute the contribution of its input representation to the output embedding E, finally giving us an updated output embedding E. Let's call it E prime. Which is now informed by both the target text context and the source text context. And the next step proceeds as below, with the computation of the dot product being this output embedding and the an embedding vocabulary matrix to finally obtain a prediction for the next word in a sequence. And the explanation actually I provided so far, it's actually simplifying things by omitting that the learned components of the attention mechanism are actually 4 weight matrices, which map the input and output embeddings into different embedding spaces for the purposes of computing the attention weights and for the purpose of updating the output embedding. Specifically, we actually create a query vector from the output embedding using matrix WQ, as you see on the left, on the right part, and a key vector from the input embedding using WK. And the dot product of these two gives us the attention weight. And this attention weight is applied to a version of the input vector modified by weight matrix WV, just the value. And this is the input value vector. And finally, the weighted sum of all the value vectors is mapped back into the embedding space of the target embedding matrix WO. And to recap, we saw this attention mechanism from encoder-decoder, sequence-to-sequence models. But now we're going to introduce this notion of self-attention, which is between encoder-encoder or decoder-decoder only attention. And each word attends to each other word within the input or within the output. Yes, and having explained this notion of attention, we are now ready to understand what is actually happening inside these machine learning models. So what is behind those boxes that we call encoder and decoder? This is a transformer architecture that consists of an encoder and a decoder box. And now we're going to see what is behind those boxes. This is the well-known transformer figure with all the different mathematical equations happening inside the model. And we have an input for the encoder, which is in our case 3 + 8 equals. And as we explained before, we get the word embeddings for this input and meaningful representation for each word. And we can actually assume that these steps are pre-processing steps. We just handle embeddings. And we also have the same in the decoder. We have a decoder input where we actually convert the Spanish text to embeddings. And the goal is to generate the text sequentially. So after generating tres más ocho son, we want the output to be 11. And in this post-processing, we process the number back to words. And the models actually assign a probability score for each possible word and generate the highest probable word. But let's take it step by step now, starting with the self-attention. So we have self-attention both in encoder and the decoder. We have an encoder-decoder cross-attention, and we have the neural networks. Starting from the self-attention part, it's what we basically already kind of explained. We have a query vector and a key vector and a value vector. These vectors are created by multiplying the embedding by 3 matrices. Let's simple it down. These matrices, we train them during the training process, and you can see these query, key, and value as 3 different views of our embeddings. Let's say right face, center face, and left face. And so starting with this self-attention, for each word, we create a query vector, a key vector, and a value vector. And the next step is to calculate the attention score between the query and the keys. And then we take a softmax, we normalize the attention scores and take a weighted sum of the values. And as you can see in this result, this results in the query seeing or paying attention to specific values more than others. And what the add and norm corresponds to is to the residual connection that adds the input of each layer to the output. And the norm refers to layer normalization. And you can, think about it as operations that we use to smooth out those numbers. And why it's called multi-head is because it performs self-attention. You can assume it multiple times and in parallel to combine these results. So in the decoder, we also have a very similar mechanism, and it's also multi-head, but we mask the future words so that the model predicts them one at a time without knowing them. That's the only difference between the encoder and decoder self-attention. And now we saw that self-attention is when keys and queries and values come from the same source. But in the decoder, we also have the type of attention that looks more like what we saw in the start of this talk, where the keys and values are drawn from the encoder and the queries are drawn from the decoder. And this is what we saw before. Okay, now we have all the numbers and their importance. We have for every word in our input and our output, we have how important are the words. But how does the model learn that? This is why we need those neural network blocks. And we applied the feed-forward layer to the output of attention, allowing the model to capture more complex non-linear linear relationships and higher level features and dependencies within the sequences. So this is how the model learns. And with transformers, language, and now actually, okay, we finished. This was it. We saw the self-attention, we saw the cross-attention, and we saw the neural network part. And overall, with transformers, language modeling performance improves smoothly as we increase model size, training data, and compute sources altogether. And this parallel relationship has been observed over multiple orders of magnitude. And if we continue scaling up these models without changing the architecture, it raises these questions that could we actually achieve human level performance if we keep increasing But of course, computing all pairs of interactions means that our computation grows quadratically with the sequence length. And this is why we need more GPUs, meaning more compute, more resources to run these models. And this is actually a problem because we cannot have infinite compute. And based on the architecture we just saw, we saw an encoder-decoder architecture. There are models that have this encoder-decoder architecture, but there are models like BERT that have an encoder-only architecture, or more recently, models like Llama, GPT, which from ChatGPT, or Gemini use a decoder-only architecture. And for example, BERT is an encoder-only model that gets bidirectional context, meaning it can condition of future words. And instead of generating left to right, we mask out tokens randomly through the sequence and we try to predict them. But we don't want to bother you with all this architecture. Usually you just get one of those models and you can choose if you want a small or a bigger model. And basically what this means is that we have more stacks of encoder blocks, we have higher dimensionality. And of course, with bigger the models, we have bigger performance. But as we said, we have a GPU problem because we are now training huge models on tons of GPU cards, and this training can take days, even months. So it is useful not to start from scratch every time, not to pre-train from scratch. And this is the difference between pre-training and fine-tuning. And we can, yes, train a model from scratch on a lot of plain text. But then we can also reuse this model on different purposes. And still, depending on the specific task we want to solve, we might want to tune the model parameters a bit to make the model tailored to the nature of the data and the task. So we can fine tune on specific tasks by using task-specific data. In our case, our data would be Spanish text. And in this, and I mean, okay, depending on the architecture, it's not always predicting the next word. But as we said, for example, BERT masks some words. But yeah, let's not get confused with that. But the importance is that we can fine tune on specific tasks using specific data. And we use usually a lower learning rate to prevent catastrophic forgetting. And we also train for a few epochs for a good pre-trained model. That would be enough. So the last thing I'm gonna talk about is parameter efficient fine-tuning. This is a technique that aims to improve the efficiency and effectiveness of fine-tuning large language models by reducing the computational resources required during the fine-tune process. And there are many different methods we could do this. For example, we could pick a subset of the parameters and fine-tune only on those. For example, yeah, the top K layers of a deep neural network. We can use the adapters method to add additional layers that have few parameters and tune only the parameters of those layers and keeping all the others fixed. Or more recently, LoRa was introduced where we learn a small delta for each of the parameter matrices with the delta chosen to be low rank. And also prefix tuning. This is another method for a transformer language model where we pretend that there exist many tokens that came before the sequence and tune the keys values corresponding to those specific tokens. And overall, the difference between parameter efficient fine-tuning and the stutter fine-tuning approach can be summarized in a table. We have one goal in parameter efficient fine-tuning. We want to have limited data and computation, while in a standard fine-tuning approach, we have a lot of, we assume that we have a lot of data and computation. So yes, in parameter efficient, we have a small data set, while in standard fine-tuning, we have a larger data set and smaller training time on one hand, longer training time on the other hand. And this means that we use fewer resources for the parameter efficient fine-tuning And actually, this approach is less prone to overfitting. So this means that the models do not actually memorize all the training data we have. They are better at generalizing to new data that they have never seen. While in the fine-tuning approach, the models can overfit. As the model is not excessively modified, it can actually memorize the patterns in the training data. And then when encountering unseen data or unseen Spanish words, for example, it will not perform as well. And lastly, the training performance. I mean, with parameter efficient fine-tuning, we do not have as good results as with the standard fine-tuning, but it's still a good approach that many researchers are using. And I mean, the final part I want to highlight is that, yeah, overall, we saw this complicated transformer architecture, which of course, it can be too complicated to implement from scratch. And this is why you don't have to implement it from scratch, actually. We usually just take an already pre-trained model and we evaluate and we train it, fine-tune it, and evaluate it on specific tasks. And if you ask, okay, where can I find those models? Where some of them are open source, and you can actually find them in this Hugging Face platform that will be explained later on. And you just can take one BERT model or one llama model that is open sourced, and we can actually fine tune it, get access to the weights of the models, and it's also free to use. But there are also closed source models like GPT-4, which is the model behind ChatGPT, or Gemini, where we actually not only we have to pay, but we do not actually have access to inside of the models, let's say. So yeah, that was it. I actually realized I was too fast. But I think you just got a general idea now of attention and transformers and the difference between training and fine-tuning and parameter efficient fine-tuning. Important part is just to get the general idea, and there are of course more material and video online of more professional people that can explain those concepts in a very simple way, and it depends how deep you want to go on these concepts. So I guess we can move to the next part, which is computer vision.
Let's have time for questions.
Okay.
Yeah. Okay, so there are a few questions here in the YouTube channel, and some of them are they are regarding the morphological inflection task that is posted on our website. One of the contestants is wondering whether following the provided code they couldn't reach the 48.8 accuracy that was stated in the original notebook. Could it be there something that they are overlooking or doing wrong?
Okay, so
Any ideas?
I mean, we haven't heard this from other people, so I'm not sure if they are doing something wrong or not, but I think they are more than welcome to reach out to us with email and actually explain the problem they're encountering, and we can of course help them, because I'm not sure if this problem with the notebook, because we didn't have any problems when we were solving it ourselves or the tester users. So
Okay, and
uh,
there is no way that you can know what is wrong with their
with their
okay.
implementation, yeah. So
Yes, with
they
their
can always send
implementation.
us, yeah, but they can always send us an email, like even share their collab if they have changed anything in their notebook, and yeah, ask us, either me or Jova, we will both gonna reply immediately.
Okay, thank you. And actually, it's about the same task. It appears that the warm-up task is not finished. It finishes with "and" something. So they are wondering whether it's correct or not. And what are the criteria for evaluating the final report, whether the score depends on test accuracy.
I actually now want to open the collab to actually see the deliverables, what it states. But I'm sharing my screen and I don't know where I can find it.
Okay, so maybe you can think about it during the next lecture, and we give more time later to
Yes,
so
because
that you can answer.
yes, because this was the task created by Yova, not me.
Mm-hmm, mm-hmm.
So I mean, I have to check the collab to see. I don't
What's
remember.
in there?
Yeah, I don't remember by heart now, but I'm pretty sure it mentions the deliverables and what is expected. Yeah, I can't find the collab on my. Mm, yeah, I don't have. I'm sharing my screen, so I can't. I unless I stop sharing and try to search the collab. Yeah, should I stop my sharing my screen and look for the collab notebook?
Okay.
Um, okay, I have it. Um, yeah. So we want you to deliver your code, which means that the notebook you have been using or any Python file you have. We want the score, the model accuracy on the test set. And in this task, we would want a report around 300 words describing the changes you made to the model architecture, the data preprocessing, the training procedure. So this means that how we're going to evaluate this is not based on the quality of your code, but based on the results and the approach you used. So how high is your model accuracy is one part that will be evaluated, for example, in this task. And the other thing is how you describe what you did and how efficient is what you did. So I think these are two major evaluation um, criteria, the score and the approach that you use. I hope this answers the question. You can hear me, right? Should I share my screen again? No, I don't know if there are any follow questions. Just replied this question about the morphological task. Yeah, I just highlighted the deliverables and how we're gonna, what is important and we're going to take into account for the evaluation.
Okay, thank you. People are still wondering about which GPT they can use, which version. Some of them believe that there are parts of GPT-4 and 4.0 that are free and available. Can you clarify that?
So do they mean in general in the final, in what tasks? Because so there are GPT models that are for free, like GPT-2, of course. But the latest GPT-4 models, they are not for free. You can get some tokens from OpenAI by creating maybe an account. They used to give some free tokens. But I'm not sure where exactly we specify the GPT for what tasks they're asking where to use the GPT model. Is this
they haven't specified that, but let's say that everything that is free of charge they can use.
Yes,
right?
exactly. Of course, they can use everything that is free of charge from this Hugging Face platform that we're gonna see in a while. For example, yeah, yeah, this notebook uses the T5 model that is based on the presentation we just saw was an encoder decoder model, and it can be found on Hugging Face, T5 Hugging Face, and then it's there, and they can use a T5 model, they can use a GPT-2 model, it's there. I mean, it depends on them, what they want to do, what is the task, but yeah, these are the models that they're going to use, or BERT. Some people, oops.
Okay, thank you. And I think we don't have any more questions for now, so let's just continue with our next lecturer.
Hello, everyone. Hope you can hear me. I will now share my screen. All right. So welcome, everyone, to this first part of computer vision. In this first part, we're going to cover some more basic topics in computer vision to give you some background. So we'll start with some basic work with images, how we work with images. Then we will extend those operations to convolutional neural networks. We will discuss encoder-decoder architectures through autoencoders. And then I will give you some examples of generative models. Okay, so what is an image? If you look at this black and white image, it's just a table of numbers with a certain width and height. And at each position in this table, which we call also matrix, there is a value which we call the intensity value, which is between 0 and 255 in integers. And each of those values is an intensity of the light in that particular position, at that pixel. So, of course, for black and white, this is enough, but for a color image, we need multiple channels, so multiple values per pixel. And so we have the common representation that we have is one channel for each color of the RGB colors. So you can see different channels here of that color image that after combined together, we get the RGB. There are many different color spaces, but the one that we use most commonly is the sRGB, and this is how we usually represent our images. In addition, we will have to do some operations on this image to prepare it for input to a network. And we usually scale from 0 to 255 to 0 to 1. And then we do some sort of normalization, which we call input normalization. What that means is what the network can really benefit from is to have its values centered at 0 with values varying up and down in the range between -1 and 1. So we're going to normalize the image in such a way that its values are between -1 and 1, centered at 0. In addition, different networks have requirements for different input size. So we're going to resize that image. And also, we can use image augmentation. So what a common problem is in computer vision is if you have a fairly small data set, you are going to quickly overfit on it, as you already know from the ML lectures as well. So to have a bigger data set just using the same data set that you have, you can just take one image and change it in some way, like change the saturation, make it black and white, do some blurring on it, all sorts of different operations. So from one image, you get many more images that you can learn a more robust representation while learning. In addition, it's quite common to also do cropping of regions in an image and use it as a separate image. In that case, one image is now a source of many images, right? So there are a few operations that we already mentioned, like, for example, scaling, upscaling and downscaling an image, but also rotation. So we can also rotate the image at a certain angle. But once we do that, the grid that represents our pixels is now not corresponding to the original positions. So all of a sudden, we need to find the color of a pixel that we just transformed, which is in between some of the original colors. So the new pixel is here. We need to know what the color is. And these are the old grid, the untransformed pixels around it. And we need to get the new color. And the simplest way to do this is to take just the closest pixel from the 4. And this is going to be the chosen color. Or with bilinear interpolation is some sort of a weighted sum of all neighbors around it to get the final color. And we call this image interpolation, this process. It's quite common. Okay, so now we are in a position where we can start talking about modifying images. So one way to do it, the simplest way to do it, is to apply a function to each of the values, the same function. For example, we can do things like change of saturation or brightness, as this example is, just additive operation. Now, this is a very simple operation. And if we want to do something more complicated on these images, we would have to do a different, different kind of function to each pixel, right? And to relate the pixels together. So it means just like in ML tasks, you would have to take all the pixel values in one function, and that function will transform all the pixels into something new. But of course, we have a lot of numbers here. We have thousands and thousands of numbers just for one image. So how to solve these huge dimensions that we have to process? Well, one thing to notice about images is they have these spatial dependencies. It means in a very small region around the same pixel, you can find the most patterns on it. And then you can relate different regions of the same image together to get an even bigger representation. And then doing that again and again, you get to the size of the entire image, and you have some sort of an understanding what the image has in it. An operation that can capture such spatial dependencies is the convolution. So to give you an example what it can do, we have this Sobel kernel here. The Sobel kernel is going to extract vertical edges from the original image, as you can see. The whiter, the higher like activation for having an edge there. And how does it work? So the kernel is this small, in this case, 3x3 little table or matrix. And we're going to apply it to the image, which is shown in blue here. I'll explain why, but we also pad with zeros. This is mostly to keep the same dimensions after the operations of the image. So how it works is we're going to take the top left part first that corresponds to the same size of the kernel, and we're going to multiply each value here. So 0 by -1, 0 by 0, 0 by 1. And by doing that, we are going to also sum all these multiplications together. And as shown here, since everything is 0 here, we're just going to get the value 0. And for that small region, we have computed that the value is 0. And in that case, it means there are no edges, right? It means 0. Once we move to the right, which is the next thing we do, we are going to have these two different values here. So 10 by 2 is 20 plus 10, we have 30. And that means that we have found an edge. We have found an edge, and this resulted in a bigger number here. So we continue doing that operation over and over until we fill in the entire output matrix here. And it gives us a description where we have the edges. And with convolution, you can do many such spatial related operations. Like, for example, you can blur an image, or you can sharpen it, or you can even do the brightness, the ones that are not spatial, right? The brightness, saturation, you can represent them as convolution. And the idea is now to have a network that is able to learn a kernel. So the kernel will transform an image into a feature map, and the feature map is going to, like as the name suggests, represent some sort of aspect of the image, some feature of it. A feature that is useful for solving the task at hand. So we're going to have a weight for each of the values in the kernel, and these are going to be our learnable parameters. So a convolutional network consists of convolutional layers. It has multiple of those kernels, which we also call filters. It has a certain size of that kernel. Here is 3 by 3, but it can also be 5 by 5 or 7 by 7. There is this padding, and the padding is used since once we do the operation, we're going to lose some rows and columns on the output. As you can see, the top row and the bottom one is lost, for example. And this is why in advance, we are going to fill in with zeros to make sure that we don't lose this dimension. So the output is the same as the input. So we also have this stride parameter, which is just the step size. As you see here, the step size is 1. So we move the square by 1, but we can move it by 2 or 4 or different number, which is going to result in a smaller feature map, but maybe with some information missing. Of course, we have activations, and we have these pooling layers, which are supposed to reduce the feature maps to smaller dimensions. Because just by using convolutions, we're still going to have a lot of pixels on the output. And we want to process less amount of numbers in the end, because it's computationally expensive. So to do that, we have, for example, the max pool operation, which is going to divide the feature maps in different regions, in this case, 2 by 2. And we're just going to take the maximum value of each region here. So the intuition here is these are activations, these are certain features, and the higher the activation, the more related to the task at hand the feature is. So we just take the activation of the entire region as the highest activation of a feature inside. But there's also other kind of tools like average, which does not perform as well, that well. So we also have normalization layers, which are also probably familiar from the other MLP networks that you have already heard about. But the basic idea is if you have many layers on top of each other, one layer is going to expect a certain range of numbers from the layer below. If this range changes all the time, it is difficult for the current layer to learn properly. So normalization makes sure that this range stays constant during training. Also common is to use dropout layers. They provide regularization. What that means is it is quite easy to overfit on images if training for a long time. And in order to prevent that, we're going to set some of the features to 0. And in that case, the patterns that are part of the overfitting are going to be not there in this particular case where we set it to 0. So it will still have to be an effective algorithm even in these cases. And so far, we have all the components for a network that analyzes an image. But if we want a CNN that can generate an image or manipulate an image, we will need to somehow enlarge the features to an image size in the end. So this is where we use transpose convolution. It is a convolution that is capable of enlarging the input features to a larger space. How it works, just really quickly, is if you take this value from the first value from the feature map that is now input to the transpose convolution, and you multiply it to a kernel, to every value in a kernel, you're going to get a certain result in the end that you can place on the top left side of this bigger output matrix. And if you repeat this process over and over again with all the values, and this square will be moving together with the position, which will take the activation from here, and you sum all of these values together, you end up with output feature map that you're going to use. And this is used quite a lot for like generating the final images, at least in convolutional neural networks. There are also many other kinds of convolutions, but for the interest of time, just move forward. There are many, many, many different convolutional neural networks, but I'm just mentioning the base ones. Of course, there's newer and more efficient than this, but I think really need to know about the base before you continue on the other ones. So VGG is the architecture with first deep CNNs that appeared. And as you can see, it consists of multiple convolutions followed by an activation function. So just the ReLU. And doing that over and over again, you decrease the dimensions of the features. So you don't have this huge amount of numbers here to process, but now they're processed in a much smaller space. And then you can now just use fully connected layers on top to solve your tasks. Then you have the inception models. It's a family of 4 models, but what is most important in them is they combine different scales of convolutions together. So different scales mean different filter sizes, 5 by 5, 3 by 3, 1 by 1. And in that case, you can create features that are relating multiple scales. So features between different scales of patches of images. And that led to quite a high boost. In addition, they're creating this really efficient architecture where they use 1 by 1 convolutions to decrease the filter size, the feature map size, the channels in the end, and many other additional improvements to make a very, very deep network. But when you build a network, a CNN that has many, many, many layers, what you will encounter sooner or later is the vanishing gradient and an exploding gradient problem. It means that the gradient, when you get it lower and lower to the initial layers, can grow really small or really big, which is a problem for learning. It's a problem for training. So to solve this problem, the authors of ResNet introduced those so-called residual connections. So you have a number of layers, and you're going to skip them over with a connection from the input just before them. And you say the output here will be X plus whatever the output of all these layers is. And in that case, you can propagate the gradient through this skip connection here, through this identity here, which really helps for the vanishing gradient problem. All right, so we move to a little bit of a different topic here. So we have dimensionality reduction. This is a task that imagine that we have a data set with k data points, right? Different entries, many entries. And each of those entries, these data points, have n dimensions. So if you take the examples on the right, you have a certain position on Earth. So you have latitude, longitude, which day of the year we're observing things, and how many daylight hours we have on this day there, and what is the temperature and weather condition. So this is an example of one sample from a data set of many such samples from such data set. So now the task is to decrease those dimensions, those 6 variables, to a smaller number of variables, in this case 3 variables, but not losing the least information possible. And if you think about it here, how you could do that, you have daylight hours, which you can perfectly calculate from the day of the year and where on Earth we are. So you can kind of get rid of that. Once you have many samples, you have the opportunity to learn how to compute this. And you can say for temperature and weather condition, maybe you also can find a pattern given the position on Earth and the day of the year. Of course, you will expect that you will lose some information because temperature varies during different years and weather conditions as well. But this is part of the price to pay for reducing dimensionality. And how this is usually solved, how this task is solved, is you give the input to a method that is going to reduce the dimensions. And then there is a decoder, so a certain method that is going to increase it back to the same dimensions. And you want this reconstruction here to be as close as possible to the input. Now, this is a very simple way to do that. It's a method called principal component analysis. I'm not going to get into the details, but imagine we have a data set of words and we have 2 variables to represent them. So the number of letters in the words and the lines of the definition in a dictionary. So we have 2 dimensions and where each of them falls in. So if we have this, then there is this PCA method, which based on eigenvalues and eigenvectors, doesn't matter in this case, is going to find these so-called principal components. So these are, this is an axis that is going to preserve the most information of this data set. What does it mean? It means that if you look at the direction of this axis, the range within where the data falls in on the action is the biggest possible. So if you start projecting words onto this axis, you would have the biggest possible range of values here. And actually, this is a very good way to represent a certain word with one number. You just project the number on the line and use the number that you have, the distance from the 0, as your encoding. And we have encoded 2 numbers into 1. Of course, there will be some loss of information, which would be evaluated by the distance to this axis. So PCA is a linear method, and you also know about another one, which is linear regression. And as you see, just fitting a line to the data is not the best way possible to lose less information. So if you fit a nonlinear function to this data, then the distances will be smaller here, which means smaller loss of information. And how that works is with MLPs, for example. So you give your data to an MLP, which is going to be a nonlinear function now. And this is the encoder. It's going to encode it to this representation here. And the decoder is also an MLP that you're going to learn. So in order to learn, you need the loss function, and the loss function is simply a comparison between the reconstruction and the input. So you want the reconstructed output to be as close as possible to the input. And this is done by mean square error. So you just take the square distances between each dimension here, between each variable, and you sum them together. So how does that translate to images? Right? Because we were just talking in general about variables. We are looking at data set with 6 dimensions, right? 6 variables. And now we have an image of for an image of 128 by 128, we have 50,000 values, right? How do we encode this? Well, in a very similar way. Instead of an MLP, which we've already discussed to be quite inefficient for images, we will make use of the spatial dependencies in an image by using a CNN. So we're going to give all of these 50 values organized as an image to the CNN, which is going to extract us a very small representation, let's say 512 numbers. And then the decoder, which is again a CNN, will be a reconstruction. We'll give you a reconstruction. And the loss is the same. So this is how autoencoders work for images. In addition, you can make the task a bit more difficult, and you can make the input noisy. So you can add some noise to it, and you have the exactly same task. And the idea is that in the middle, you learn a much robust representation. But this already gives you an idea that you could possibly have different images on input and output. And then it would no longer be an autoencoder, which requires that the same data point to be on the input and output, but the same kind of, the mechanism is the same. So you're going to extract features from the encoder, from the incoming data here, that is really relevant to the task at hand, which is to generate whatever image you want here. And that is the intuition I really want to give here. Now we are going towards a similar but quite a different task, the task of the generative models. So while with autoencoders, you give a specific sample from a data set and you want to reconstruct it, with generative models, while training, you will give images in the training data set. And afterwards, you will be able to give a random noise vector. And this random noise vector, the decoder can map it to a new unseen image, unseen in the training set, unseen anywhere, that is going to be realistic. It's going to follow the distribution of the training data. Okay, how do we do something like this? Well, there are multiple models doing that, and we're going to first start with generative adversarial networks. The idea here is that we have 2 different submodels, the generator and the discriminator. And the generator's goal is to generate a very realistic image according to the training dataset. And the discriminator is going to try to find out if an image that is receiving at its input is generated or is it real from the training set. So as you can see here, we sample, while training, we can sample an image from the dataset and we can give it to the discriminator and it has to say that this is real data. Otherwise, we take a random noise vector that we give to our generator, and the generator is going to give us some fake data, which is the generated data. And this is also given to the discriminator, and the discriminator has to say this is fake data. So the better the discriminator becomes, the better the generator becomes at generating realistic data, because the gradients flow from the discriminator to the generator. And what is important is we have this function here that the discriminator is maximizing while the generator is minimizing. So they're playing this game where they will converge to something in the middle, and then there will be the optimum. Okay, but with this method, afterwards, you would be able to only give a noise vector and get an image. But what if you want to have more control? For example, you want to give a certain sketch of an image and get a realistic image of it, right? There could be many different conditions, as you can see here. Now, in order to do that, you just give a condition. This is why we call them conditional GANs. And the condition is given both to the generator and the discriminator. In this way, the discriminator can also check if the condition matches this image. And if it doesn't match, then the generator is not really conditioned on it, right? It doesn't really look at it. And in this way, you receive realistic images, but you can also control them. Now, this is quite an old method. These days, generative adversarial networks are not by themselves used that much, but you will see a lot of use of this discriminator with this concept of a base model and the discriminator playing this game for a more realistic image. It still happens even with some transformer models. Now, another model that is quite used these days is the variational autoencoder. It's usually used for extracting representations of images that then they are passed to like a transformer that works on them, operates on them. So how does this one work? So you have a data set that has a certain distribution. What that means is there is a probability function over the space of all possible images. And for each image, you have a probability. Is this a real image or is it not really likely? So if you get just random noise, it's probably not a realistic image. But if it's like an image of a tiger like this, you'll get a high probability from here. Now you draw a data set from there, but you will not know this distribution, and you're going to try to build your own here. The encoder is going to take this input image and is going to try to find parameters of a distribution. So this would be the mean and the variance of multivariate Gaussian distribution. And so given these parameters, the claim here is that using this distribution, you will be able to get this image that you sampled from it. And so at the same time, we want to be close to some sort of initial prior distribution. So our model doesn't go haywire and spreads the images all over the infinite space, right? So this is also a small condition that we have. And what the output, what the decoder will do is if I take a certain now code vector from this Wern distribution, so I'm going to sample some sort of numbers that are going to be my representation of the image in this space. I want to really be able to, with a high likelihood, to draw this image from it. if this Z gives me a distribution, I want X to be really likely, right? And so the goal here is to, in training, to maximize this likelihood of maximizing this X being generated by Z, which in turn has been generated by X in the first place, right? While training at least. But this turns out to be intractable. It's a very, very difficult problem to solve. So what they found is, since we want to maximize this, if we find another function that gives us a smaller number than it, then we are still fine because we can maximize this function as well. And this is the evidence lower bound that they have found as such function, and it works quite well to represent images in this way. So how does it work in inference time? We're going to, again, completely get rid of the encoder. And now we have this space here that is already learned, that we can draw samples from it. And we usually pick the initial distribution that we picked. So it would be the normal distribution with mean 0 and variance 1. And then we get a new image. That's how it works. But again, what if we want to have a certain condition? So what if I want an image of a tiger in specific? That means that I need to have some sort of a label, some sort of condition here that, just like with generative adversarial networks, I'm going to give to the encoder and to the decoder, right? So there we gave it to the generator and the discriminator, and the logic is exactly the same here. I want to give it to the encoder so it knows to put it in a place in this space that it's learning that is related to this condition. And the decoder should know what the condition is, so it knows what to generate exactly, right? So this is the logic behind it. All right, and a version, well, it's quite far from a regular VAE, but it's a vector quantized VAE. And what the concept here is that instead of having, instead of learning distributions over this large infinite space, you instead have a finite set of vectors that you're going to learn. So what this is called is like discretization. So it looks like this. Your encoder is going to produce some position in space, and then your vectors are kind of spread in this space. And based on the distance from whatever the encoder gave you, you're going to take the closest vector or some neighborhood, like a few of them. And then you just take this vector and give it to the decoder. And the decoder should generate a very, very like similar image or the same. And the idea is each of those vectors, while training, they will start representing different kind of images, like different like categories of images. And in the end, like having different distances between them will represent different like a manifold, continuous manifold of images. This method is used quite a lot for building representations of images, as I said before, and then giving it to another model. Instead of giving it thousands and thousands of pixels, now give them just a few features that is going to represent the entire image. And lastly, I want to discuss the UNet architecture. The UNet architecture is an encoder-decoder network that is probably the most widely used these days. It has been used for years. It looks like this, like the picture on the right. And the idea here is that you have a number of downsampling blocks that you can see here, like one downsampling block, another one. It consists of multiple convolutions. So each convolutions will give you more and more complex features after each convolution. And then in the end, you want to decrease the dimensions of this big feature map in the end. So you're going to apply a pool and you repeat again and again and again. And here at the bottom, just like with autoencoders, right? This is an encoder-decoder, you get different input and output, but the idea is the same. You get a very compact representation here of the task-related features on the input of whatever is important in this image to generate the output image. And then you start the reverse process. It's the upsampling blocks here, which instead of max pooling, right, because max pooling is for decreasing, we have the transpose convolution for increasing the size. And what is very important are those skip connections that you see here. So the skip connections, what they make sure is while you decrease the feature size here, you're going to lose some small details from the original image and the features along the way. And if you want to preserve them, you just give the features directly to the block that is increasing your features. So then these small details are still preserved. This is what works best in practice. And UNet has many variants. So on top, you can see some of them, which are mostly related to where the skip connections go exactly, not just linearly like with the original one, but in some more complicated ways, even adding new blocks in the middle. But an important version of UNet is the one used in diffusion. I'm making a bit of a spoiler from the next lecture here. But the idea is to include an attention layer between those different blocks here. And the attention layer is going to make sure that an input text information is also combined with these image features here. And for diffusion, we have text that tells you what you want to generate in the end, because you just write it down and it gives you an image of it. And this is the part where you connect the text to what is generated. And the same attended features also go through the skip connections here. And I believe that's all for the first part of computer vision. If you have any questions.
Thank you very much for this interesting lecture. So far, there is only one question, how and whether they can get the presentations from the slides from the presentation, our participants. Can
Okay, so
it?
I believe that first of all, before we share it, this entire stream will be uploaded in YouTube, right? So
Yes.
that is one source of where they can get this information from. And the slides, I think we can also provide, but we'll have to arrange how to do that exactly. And maybe somewhere on the website, we can include the slides. I'm perfectly fine with sharing the slides.
Okay, so let's say that we will share the slides and we'll let you know, guys, how we will do that when the jury decides. Okay, thank you very much.
Yes, please. Let's continue.
So continuing on, let me share my screen. Can you hear and see? Okay. Okay, very good. So I will continue the next part of computer vision, which is part 2. And in this block of the presentation, we will look at additional methods, particularly those which are very modern and more or less ubiquitous nowadays in traditional and deep learning based vision. So in particular, we'll look at the vision transformer, which has become kind of the default backbone for many, many models. Additionally, we'll look at diffusion, the diffusion paradigm for generative modeling and for image generation. This is pretty much what you see in all kinds of text-to-image models nowadays. And lastly, we'll discuss briefly about multimodal architectures. So these are architectures which work with different modalities of data, for example, text, image, and so on. So let's start with the VIT. So we saw in the NLP lecture that attention is a very useful thing to have in your model because it offers an inductive bias. This inductive bias represents the idea that we should interpret tokens based on the semantic context with respect to other tokens in their neighborhood. And this turns out to be very useful. So the question comes, is it possible to apply this inductive bias of attention also to vision? And in principle, to follow the same exact process that we followed in NLP, we need to solve two tasks. We need to define what is a token, what will serve as a token, and we need to define how we will extract tokens from an image. This is basically the tokenization process. Now, the computer vision community has converged on how to do this, and the blueprint for how to do this is given by the VIT architecture. VIT stands for Vision Transformer. And according to the VIT architecture, a token is defined simply as a patch of pixels. For example, a patch of 14 by 14 pixels, along with their values and channels and so on. So this is a token in the context of vision. And for the second task of tokenization, our process will be to simply cut the image into many non-overlapping patches. So let's see the vision architecture. As we can see here, we have an input image, which gets cut into multiple square patches of pixels. So this is one patch, this is the second one, third one, fourth one, and so on. They are non-overlapping. Then they get flattened, like we see here. Flattening here means that we lose any two-dimensional structure to them, and we just treat them as a sequence of visual patches, like this. So the intensity, the pixel intensity values from each one of these patches gets projected using a linear layer to obtain an initial latent vector, which represents this patch. And this happens in parallel with all the patches. Subsequently, we apply what's called positional encodings or positional embeddings. These are additional features which come from the position of each patch. And it's all very similar to transformers in NLP. So all of these embeddings, they get fed into a transformer encoder, which has self-attention and cross-attention, and in principle has the same structure as in NLP. And finally, we have a task-specific MLP head, which may be for segmentation, for prediction, for classification, all kinds of tasks are possible. So in code, the architecture is very straightforward. The image comes in. This is the image. We extract patches, also known as visual tokens. To each patch, we add the positional embeddings, which contain positional features. So where this particular patch is compared to the whole image. All these tokens, which have been augmented with positions, are fed to the transformer. And at the end, we have a bunch of layers which predict whatever is of interest, for example, classes. How does the tokenization work? It's very simple. It's literally, as I said, just cutting up the image into patches. So what happens is that you receive a stack of images. So B is the batch size, C is the number of channels, RGB. This is the total height of each image and the total width. And the total height gets cut into the patch height, usually 14 by 14, 16. So this is the patch height, and this is how many patches fit into the total height of the image. So same here, you cut it this way. The total number of patches gets flattened after this rearrangement. So that's why you see here H and W, and all the pixel values within the patch, they form the dimension of the token. So as I said, the problem is that just a single patch here, the model does not really know that this patch is in the top left of the image. So that's why we need to augment this patch with positional information. And we follow the same logic as in NLP. So we have positional encodings, which are sines and cosines of the index of the patch. And these features can be pre-computed, they can be stored beforehand. So it's they're very efficient to calculate, and we just add them in an additive way to the actual patch tokens. So, and pretty much this is all that is important to say about the VIT. So I'd like to stress that VITs work by mixing information from one patch token to the other patch tokens. And typically, the gain in performance comes from precisely this, establishing correlations between different visual tokens from one end of the image to the other one. And this is very important when it comes to image generation, because if you want to generate an image of a person, of the face of a person, obviously you want to have the eyes of the person be of consistent color. They want to be of the same color. So in this case, you want the visual features for one of the eyes to attend and to sufficiently mix with the visual features of the other eye. And there are all kinds of symmetries. For example, faces are symmetric. So in that sense, you need your visual tokens from the left part of the image to attend to those corresponding tokens on the right side of the image. In general, smaller patches lead to more tokens being processed, which increases computation time and inference. More transformer layers, as in NLP, typically improves performance, but also increases the inference time. And lastly, if we increase the latent dimension of each patch, so this would be basically the hidden dimension here in the transformer. This is like providing more power to the transformer, so the representational capacity of the model increases at the cost of being slower to infer. So VITs, as I said, they've become more or less ubiquitous in computer vision. They have found applications in all kinds of tasks. So here I would like to highlight, for example, object detection. So object detection is the task of locating and identifying any objects of interest in the image. So we can imagine an architecture in which we apply a convolutional neural network first to the image. We extract some convolutional features. which are, again, two-dimensional feature maps. So they can be, in principle, cut into these visual patches, and they can be fed into the transformer encoder. So in that case, each of these patches will attend to all the others. And throughout the layers, information will get sufficiently mixed together, and this will produce patches which are more meaningful, more semantically meaningful. Typically for the decoder, we can have a similar kind of scheme where we start with some queries, and each query attends over these augmented processed patches from the encoder. So this is a very, very typical kind of design pattern for these kinds of models. And at the output, we have, again, a task-specific head, which predicts the bounding boxes and the classes of the objects. Okay, so VITs are very useful, and they have also found applications in image generation, specifically in diffusion models. So let's now discuss the second subtopic of this block, which is diffusion. So I would like to highlight that diffusion and, in general, image generation is intrinsically tied to denoising. So you can imagine that I give you here a noisy image, and your goal is to denoise it. So the thing is that if you select one of these green pixels, you don't really know what the actual pixel value should be. So, of course, you can make a very intelligent guess based on the surroundings, based on prior knowledge from a data set and so on, but you don't really know what the value should be. So you can see that even this kind of denoising can be thought of as generation, although very constrained. And you can see that if the noise of the image kind of overwhelms any actual signal, so if we have so much noise that this fish becomes invisible to us, then coming up with a clear image is much more like the generation that we are used to. So this is much more kind of like generating an object out of nothing. And precisely this is the strategy that diffusion models follow. So in diffusion models, we will train a network to denoise from noisy images to less noisy images, and preferably to clean, entirely clean images. And the thing is that if we start from a noisy image like this, where you can still see the outlines of an object, like in this case, a person, then it's still generating a clean image. That's what we expect from the model. And if we start from something where the noise completely overwhelms the image, then it should be able to generate images which are entirely consistent and more diverse with this initial noisy image. Yeah, so diffusion in general, this kind of strategy requires three things. It requires a proper dataset and a model. It requires a forward process, which typically adds noise to the image for the purpose of training. And it requires a reverse diffusion process, which is what we use to generate an image by denoising an initial noisy version of it. So the forward process, we can see it here. We can start with a clean image, for example, x0, and we can, in many steps, iteratively add noise to it, such that it becomes more and more noisy. So we'll do this in a very controlled and parameterized way. So we'll set this process to run up to t steps. Typically, this is 1000 in practice. And this kind of process forms a stochastic process because it's an ordered sequence of random variables where the next one depends on the previous one, which depends on the previous one, and so on. So the forward process is parameterized from 0 to t, from time 0 to time t. And depending on various mathematical conditions, we can get some very useful things and properties out of this process. So in particular, if we want to sample this noisy image at time t equals 3, we don't really have to run the process for 3 steps. We can calculate it directly. This comes from the mathematics of the process. We don't have time to go into the details here, but you have to take my word for it, my word, and believe me that it's possible to skip these steps and sample directly from each point. Similarly, another useful thing is that at the end, again, depending on the mathematics, at the end, it's guaranteed that this noisy image will be sampled from a standard Gaussian distribution with mean 0 and standard deviation 1. So this is the forward process. Now, the backward process is, again, slightly more convoluted in terms of mathematics, but it's still fairly straightforward. What we want to have is we want to have something like this. We start with a completely noisy image sampled from a normal distribution with mean 0 and standard deviation 1. So this is the noisy image at the last time step, t, and we want to periodically refine it up to time step t0, where we will eventually get a clean image, as seen here. So how do we do that? The thing is that, again, coming from the mathematical parts of it, the denoised image given the next time noisy image, next step noisy image, is not Gaussian. So this distribution is very, very complicated to model. However, if we condition on the clean image, it becomes a Gaussian. And this is the strategy that we use for diffusion models. Essentially, in time step t, we have this image, xt, and the question becomes, how can we get an estimate of x0 so that once we have the estimate, we can sample from xt minus 1. And typically, the model that we will learn will be predicting the noise, which, when added to x0, will give us xt. So this is what the model predicts. The model predicts the noise such that when added to x0, we get xt. And obviously, if we can predict accurately this noise, we can just subtract it from xt and get x0. So this is the strategy that we use. The model will be essentially indirectly predicting x0. And once we have this, we just sample from this distribution, which is Gaussian. And we repeat this process for many steps. So just to show you that it's not very difficult, let's say, we can discuss the training and the sampling of the diffusion model. So at training time, we sample initial clean image from the dataset. This is x0. Now we choose diffusion time step. For example, x2. So the time will be time step 2. And this controls how much noise is added. Then we compute the noisy version of the image from the clean version. So x0 is the clean one. This calculation here gives us the noisy version. Once we have the noisy version, we give it to the model. This is the model. It's a function. And the model gives us an estimate of the noise. And this estimate gets supervised by the actual noise that we have added. So this is the loss. It's pretty straightforward. Now for the sampling, again, we start from complete randomness from a normal distribution. And for t steps from capital T to 1, we call the model, which gives us an estimate of the noise. This calculation gives us an estimate of x0. And finally, this calculation gives us a sample from the denoised distribution. And that's how, starting from this, we periodically resample and resample and resample until very gradually we can obtain images. Okay, so as you can see, this is how diffusion sampling works in practice, starting from random noise and refining this noise. We can see how the outline of an object starts to appear, and typically this outline gets further and further denoised, further reshaped and refined until we actually see something very meaningful, like an object. We can also see here with faces. So if we start with this noise sampled from the last time step, obviously we can get very different samples from it. Oh, very, very different. So if we start from something which is, again, noisy, but less noisy, so from time step 750, you can already see that there are patterns in the samples. So in this case, glasses, people wearing glasses. If we start with this noise, again, noisy, however, less noise overall, you can see that the variations in the samples are quite small. And furthermore, if we start conditioning more and more on the face of this person, we get less and less variance in the outputs. So this is all consistent with what we saw back here in this slide, that we are ultimately denoising, and the more we are denoising, the more we are generating from the sample of possible images. So in practice, diffusion models tend to be quite large. Remember that we have to predict noise, and this noise has the same shape as the image. So it's typically of the same shape as the image, which forces us to use a UNet architecture or some kind of autoencoder, but a UNet is very, very standard. It's also a slow process at test time. So we can use various tricks like doing diffusion in the latent space or adopting a more sophisticated schedule, which can in principle skip some of these steps. However, this is more of a kind of research question, how to do it in a way that's efficient. And we can also condition our generation based on text. So as we saw this diagram already. This is stable diffusion. We have the features from the image coming in here. We have the noise amount. So this would be the diffusion time step T, which has been sampled here, T. And we have text information. So text would be the prompt that you're giving to the model. And this text is ultimately combined in the cross attention of the models. there is really no other way to combine this text with the vision apart from simply sufficiently mixing the features of both. And yeah, different models obviously do the details in a different way. But this is quite standard to have the text embeddings enter in the form of keys and values in the cross extension. Okay, so let's briefly talk about multimodality. So multimodal methods refers to methods which can accept data of different modalities. For example, both an image and some text. And typically the output is also text or image. So these are very useful, obviously, because we can combine modalities and we can extract and reason about things across different modalities. So compared to unimodal architectures, multimodal methods have 3 additional questions that need to be answered. First is how to extract features from each modality. How to extract features. Second is how to fuse them. Fuse them means sufficiently mix them together such that the attentions can attend between them, for example. Third question is when to fuse them. So I won't be discussing this, but there are different options. We can fuse them earlier in the architecture, we can fuse them later. And typically all these things have different trade-offs in terms of capacity of the model and inference time. So in terms of how to extract different features from different modalities, the most straightforward answer I can give you is that each modality requires its own specific encoder. Because different modalities can be quite different. Digital images, as we saw, they're very high dimensional. They have data points which are regularly spaced along a 2D grid. Text, as we saw, is discrete in nature. Typically, we have a discrete alphabet of symbols which can generate a discrete number of sequences. So text can be, for example, very sensitive to the presence of some tokens or not. Networks, they have completely different geometric properties. For example, it's all about what is connected to what in them. So all of these things have to be encoded in a way that respects their constraints, so to speak. So how to extract features from different modalities? The question, the answer is that we do it using specific encoders for each modality. So how do we fuse then? How do we fuse from different modalities? I'm going to show you a few methods. Some of them are basic, some of them are advanced. So clip, for example, is a very early method. It's shallow in the sense that the features which we extract from the text and the image are not really fused. They are not mixed together, but we just make sure that the feature corresponding to an image is similar as judged by, for example, some kind of distance, like the cosine distance, similar to the feature from its corresponding text description. So what we want to have are features which, when compared, they give a high score, high similarity score. But when we compare the feature of this image with this test, with a different text description, these features should be fairly different. So this is intuitive, lightweight, and shallow, as I said. Stable diffusion fuses information in a slightly more clever way. So the text description comes in from here. It's provided by the user. It gets encoded into a text encoder, which gives us some form of latent vector. And this latent vector enters at many places. Enters into the cross tension, like we saw back a few slides ago. So this is a way to, again, to sufficiently mix the text features with those of the visual features. And ultimately the loss which trains these models. The loss is the kind of the thing that makes the model learn which features to attend over and which to abstract away. And finally, there are some methods which fuse information from different modalities in a very sophisticated manner. So let's say, so you can, in principle, train a transformer which takes the visual tokens from an image encoder and modifies them into the text tokens of a LLM. So this is entirely possible. It's not easy, and I just want to show you that it's possible. But this is kind of what happens. So you have image features coming in from here. You have some initial visual queries, which along with the text queries and text tokens, they get processed to obtain new visual queries, which have the same format, the same shape as the queries which are accepted by an LLM. And typically, this kind of adapter architecture is what modifies the tokens from one modality to the tokens of another one. Okay, I would like to maybe finish here, and yeah, we can discuss questions.
Thank you for this interesting talk. So far, we don't have any questions in the YouTube channel. If someone wants to ask a question, please write them in the chat. In case there are no questions, maybe we'll just let you guys continue with the next talk. And if some questions come, we'll just take them and answer after the next session.
Yeah, sounds good.
Thank you very much.
All right, can I start?
Yes, please.
All right. Let me share my screen. So, hello everyone. My name is Abdurrahman, and I'm going to give you a quick overview of coding for ML. It's gonna be a very dense tutorial, so I'm trying to give you an overview on as much things as I can, so I can go slightly faster in some slides. So here we go. So this is what we're gonna cover. So we're gonna have a very quick overview on what is Colab, and then go see what's popular Python libraries we usually use, and then have a short introduction to Hugging Face library, and then show some tools that we usually need when doing coding. So first on Colab, let me just start a slideshow. So Colab is a cloud-based Jupyter notebook. If you don't know what's a Jupyter notebook, it's just, you can consider it a web-based IDE. If you don't know what's an IDE, you'll know it near the end. So it requires no such setup and it can be accessed directly from your browser, and it provides a limited GPU access. So we're gonna cover these points now, like how to upload file, how to mount your Google Drive so you can use the data you have on your drive or save stuff, how to install libraries in Colab, and how to use command line. So let's quickly go to the Colab tab. So to mount your drive, you can simply just import drive from Google Colab and then mount your drive. This line takes care of it. And it will prompt you to enter your allowed access to Colab and so on. So I already mounted, so it doesn't show now. For uploading, you can see like this little button opens the directory that you have in Colab, and then there is the upload button. And you can upload any file in Colab. And the files like will vanish after you close your session, so make sure you save them if you want. And in able to read the file or use the file, you can easily like just copy the path and use those files. You can use in Colab the commands you can normally use with your command line. Usually you need to add the magic character and then use the command you want. So for example, cat to see what's inside the file I just copied. So yeah, so you can see the file. And you can upload any files and use them the same way. You just copy the path and add them where you want. Second thing I want to add is like how to install libraries. So normally, as you do in your command line, you just can pip install whatever libraries you want in Colab, and it works just fine. Just make sure you add the exclamation mark before it. And you can just install any libraries in Colab. As I was saying, you can also traverse your directories using the normal command lines you use with your command line. For example, if I want to move like to see what's the current directory, let's just pwd, which is like show you your current work directory. Sorry. So this is my current work directory. I want to go to the Google Drive directory, so I just use cd and drive. And now I have access to all the files on the drive. Like I can just ls, and I can see all the files I have on my drive. Another thing you may need in Google Colab is just if you want to clone some repo to use it in your code, you do it as you do it in the normal command line. Just add exclamation mark and get clone, and then the repo you want. For the GPU access, you change your runtime from here. You go to runtime, change your runtime type, and then you can either use CPU or GPU. GPU have a limited access, which is usually like 12 hours, so don't abuse it. Like just use it when you need it. When you don't, go back to CPU. All right, so this is a very quick introduction to Colab. Let's see what's next. All right, so Python libraries. So I'm gonna cover the most important Python libraries here. It's gonna be just a quick overview since we have little time, and I will have the documentations at the bottom of each slide. An advice is just like have a quick overview on the important libraries from the documentation, and then ask ChatGPT. It's the best teacher you can ever have for this kind of stuff. Just ask it about any function you don't understand. It will be very quick and easy to do. And also, if you're not familiar with Python as much, this is a very nice tutorial that you can access to refresh your Python knowledge. All right, so let's start with NumPy. So NumPy provides support for creating and manipulating arrays and applying a wide range of operation on them. You can do dot product, you can inverse a matrix, you can do a lot of stuff. It's just like whatever you need to do with a matrix, you can do it with NumPy arrays. And it's fast compared to normal Python because it's written in C and it's just wrapped with a Python wrapper. And the data type it uses is called ND array. So if you have a check dot type, this is your variable encoded ND array, so you're using a NumPy array. So the key features, it can be easily casted to and from any other data type. So you can go from list to NumPy array, from NumPy array to an image, from image to NumPy array. So this is one of the very cool features for NumPy arrays. It can be intermediate to go from one data type to another. Broadcasting, it's like automatically broadcast your variables. For example, if you have an array and you added a scalar to it, just like an array of 4 elements and you add 1 to it, it will just expand this one to be an array of the same size and add the one in each element of the array. So this is broadcasting, and it works in every dimension. Last thing is vectorization, is that one of the benefits of using arrays is just it vectorizes your code. For example, if you're doing neural networks and you do like WX plus B, instead of doing it for each data point, you can just put all your data points in a vector form and then do it in one go instead of using a for loop. So this is vectorization, just changing a for loop to just a vector or a matrix and just do the operation you want on it. All right. So the second library we were talking about is SciPy. So SciPy extends the functionalities of NumPy with mathematical algorithms and some useful functions. So it have linear algebra functions. For example, you can do eigenvalues, eigenvectors, and so almost any linear algebra operation you can think of. You can do statistics operation, for example, getting the p-value and probability distributions. And you can do signal processing with it, like filtering a signal. It's not very useful library nowadays because most of the functionality you can get it from the following library, but I just wanted to show there's something called SciPy. So the next library is scikit-learn. So it's just a better SciPy. It's built on NumPy and SciPy, and it has tons of machine learning models, and it has a lot of data sets. It's really good if you're doing basic machine learning stuff, not deep learning, like just machine learning things. So it has libraries for implementing and evaluation of machine learning models. So it has a lot of models like Bayesian, logistic regression, linear regression, and so on. And it has evaluating tools that you can use to evaluate your model. And it has data processing and feature engineering libraries that you can play with your data, so like normalize the data and so on. And as usual, like the documentation is down there. It's a really nice documentation. So I will recommend the documentation as we go on. So I recommend reading NumPy documentation and scikit-learn. They are super easy and super useful and super easy to like follow. All right, so the next one is Python, Pandas, Python data analysis library. It's data analysis and evaluation tool, also built on top of NumPy, which means it's fast. Since NumPy is written in C, it's the same. The data type it uses data frames and series. Both are tabular form. Data frame is just column and rows. It's like an Excel sheet, but like in Python. And series is just like a kind of a vector, like one row of a data frame. So data frame is multiple series. And you can use it to load almost any type of data. You can use it to JSON file, CSV, text, or Excel sheet, anything. You can use it for pandas. Like it's really nice in this regard. So the key features, you can use it for data cleaning. You can handle missing data with it. It has like some functions you can use to handle missing data and remove duplicated entries and so on. You can do data transformation with it, merge a data frame with a data frame and join them, concatenate them, and everything you can do is SQL. You can do it in pandas data frame, which is super cool. And lastly, you can do the data wrangling. It's just like having some random data that you want it to be in a decent format. You can use it later for your model, training your model. Also, pandas documentation is quite nice, but I wanted to show like some of the most used things in pandas, like personally speaking. It's just like reading a file, CSV file, Excel, and this should be read underscore JSON, just read the JSON file. And data frame.head. So we called our variable data frame. So df.head is just show you the top entries, info showing you the information is like how many data you have and so on. Describe show you statistics of the information is like what is the mean of certain column and so on. If it have null values, it's really nice to see what's wrong with your data. And also you can filter your data on specific conditions. Like I want the data that have only for example, having, if your call name is age, having people with age more than 10, so you can just isolate your data and do specific operations on it. So the next library I'm going to talk about is Matplotlib. So this one is useful for visualization if you want to look at your data, because looking at data with your eyes is just some values is super hard. So you can use it to visualize data and you can create nice figures with it. And it's simple and have wide support online, so you can always find what you need online in this one. Also, ChatGPT is super useful in it. And the documentation is quite nice, but it has a lot of things that can be tweaked, so I would recommend using ChatGPT for this one. All right, so the next library is OpenCV. So it has a comprehensive set of tools for computer vision applications. This was the best thing after slice of bread before the era of deep learning. It was doing fancy stuff in the computer vision section of life. So this was a go-to. It have function for image manipulation, filtering, edge detection, picture extraction, and morphological operations, and so on. It also have tools for motion detection, object tracking, and background subtraction. It was like the best thing ever. It was like you can have everything you can do in an image. And also it has a 3D stuff like camera calibration and 3D reconstruction. So key features, it has almost any machine learning algorithm you can use for computer vision, for example, face recognition algorithms, object detection algorithms, and augmented reality. Yeah, life was fancy before deep learning, but not as fancy as now. And also, it have deep learning integration with current frameworks like TensorFlow and PyTorch. So anyway, so scikit-learn is like have general machine learning algorithms. OpenCV is focused on just computer vision algorithm. So the next library is Pile. So it's used for image reading and navigation. It has a data type that's called Pile. So if you check your variable and the type is Pile, you're using Pile. And it's directly compatible with PyTorch and other libraries. You can literally like directly use this data type and pass it to PyTorch and it will not complain. So this is the most used command for me with Pile is just like image open. It's just like usually used to open the images in your dataset class or just do some simple manipulations on it. The tutorial is super long, so I would just say stick with ChatGPT with this one also. And for OpenCV, I don't think you would need it much with deep learning nowadays, but whenever you wanted to work on low-level machine learning, low-level computer vision, you will need it. So like don't approach the OpenCV documentation until you really need to do some low-level stuff because it's super big and super complicated. It's straightforward, but like there's too many functions and classes in it. All right, so the next library we have is NLTK, Natural Language Toolkit. So it's OpenCV, but for language, but it's slightly less overwhelming than OpenCV. So it has a suite for text processing libraries. You can do tokenization, you can do stemming, you can do lemmatization, and so much more with it as text processing. And you can do other stuff like part-of-speech tagging and syntactic parsing. And you can also do semantic reasoning. So yeah, before deep learning, there was actually some work on language, but like it boomed when transformers happened because the accuracy was not that good and we didn't have a generation model back then. So the key features, as I was saying, OpenCV is having a lot of vision algorithms, and NLTK have a lot of NLP algorithms. So it's focused on NLP algorithms. So you can have like your naive Bayes and a lot of other NLP algorithms used for classification, clustering, and so on. It has a lot of sentiment analysis, pre-trained stuff, and data sets, language translation, and information extraction. And to train the stuff, you have over 50 Corbra and Lexile resources you can load and play with. NLTK is useful nowadays also because you can do the pre-processing on it. And if you want to play with low-level stuff that doesn't require GPU, this is your go-to. It's slightly less overwhelming than OpenCV, so the documentation is nice. All right, so we finished the pre-deep learning era. Now we have deep learning, so we're using PyTorch. So PyTorch is an open source library developed by Facebook. It's widely used in academia, and it's currently getting more popular in industry. It's catching up to TensorFlow, which is interesting. TensorFlow is like the best thing in industry, but now PyTorch is going there. And it's Pythonic. This kind of are related now because TensorFlow 2 is also Pythonic now, but like back in the days, TensorFlow 1 was super hard to play with. It wasn't like as intuitive as now. So yeah, like it's still a feature. It's Pythonic. It have intuitive syntax. It looks like Python code. And it have huge community support, and it can be easily integrated with a lot of popular libraries. So the key components we're going to talk about is first, the data type of your PyTorch variables are tensors. So tensors are basically NumPy arrays, but for GPUs. So it's just like it behaves very similar to NumPy array, but it just can be used with GPUs. So that's why we use tensors. Sometimes you would like to use your tensors with CPU, so you just move it to CPU and play with a NumPy array. So this is a quick tip. PyTorch have computational graph and autograd, so it creates the computational graph for your code, for your model. So it calculates the weights for you and does the backpropagation, the partial differentiation and stuff. It does everything for you in the background, and you just click one line of code and you have your model's output done. So pretty cool. It uses something called dynamic graph, but it's not related now because TensorFlow 2 now have also dynamic graph. So the difference between static graph and dynamic graph, that static graph, you create everything at the start of creating your model, and then you just do it once and you can't change anything. Dynamic graph, it works as you go through your code. So you can debug actual, like you can see the output of each part of your model and play with it without having any errors, but static graph, you cannot do that. It has data sets, which is your class that you create your data sets on and you give it your model. It has a data loader, which loads your data set into your model. And finally, we can see how training looks like. So this is a very quick code for PyTorch. So transform is just like a library that you can use to apply transforms in your data. Usually used in computer visions, like add normalization, add some kind of segmentation and stuff. Transformers use this. Train set is like, I'm just loading a data set from the repo. Train loader, this is how you created train loader. You just load it from torch.utils with data loader. So this is your data loader, and you give it your data set, batch size. And if you're training, you want to shuffle your data so your model does not see the same class over and over at the start. It's really bad. It will cause a really bad behavior. So here is where you define your network. So you need to inherit from your nn.module, which is the base module for PyTorch. And nn.linear will give you like create a linear layer for like just a linear layer. To create a linear layer, you need to call nn.linear. So this is the first linear layer, and then we were making an MLP, so we'll create another linear layer. So this is just a simple MLP that can be used for classification. It outputs 10 classes. And you have your forward path. This is what you want your model to do. So I want my model is to take an image and make it expand it and path it to 2 MLP layers. This is a bad approach. It's not seen in just an MLP, but like, yeah, it's just showing a demo. So you take your image, flatten it, pass it to the first fully connected layer, and then applying a activation function. And then you have your first FC1 done, your first fully connected layer, and then you pass your output again to the second layer, and so on. So if you have multiple layers in your model, you can just take the output of one model to give it one layer to give it to the next one, and the next one, and the next one. All right, so we have only forward path. So where is the backward path? As we were talking about, the computational graph takes care of it. So you just define the forward path, and everything is taken care by PyTorch. So we create an instance for our class. We call it net. You need to define a criterion, which is the loss function you're going to use. For us, we're going to use cross-interval loss because it's just a simple classification task. And the optimizer, you need also to specify the optimizer. Here is just SGD. So PyTorch have all the optimizer in torch.optim. You can have Adam, SGD, whatsoever you're gonna use. So here is a simple training loop. You take your train loader that you just created up there, and you get the inputs. You take the outputs you give. So here we have only like an images that have like features and labels. So we take the inputs and labels from our train loader. You first zero grad your optimizer, so it doesn't have gradients from before. You give your inputs to your network you just created up there. You calculate the loss using your criterion you just created up there. Loss the backward. This is the autograd I was talking about. Just one line, and you're done with your backpropagation. And then you measure the steps to update your model's parameter. So we were talking about the dataset class. So this is the dataset class over the hood. So before we just was loading the data set in the train loader, and then just some 2 variables came up. So this is how it looks from the inside. So you have your get item. This is what it gets called when you have your data loader calls. So this is a simple data set, just returns a text and a label. And this is what we get rid with your data loader. Also, there's something called cloud function where so PyTorch data loader expects everything to be the same size. So sometimes when you work with text, you have different sizes and you want to do some padding. So usually you do the padding in the collab function, where you take the outputs you take from the get item, and then you just do whatever you want with the padding and then pass it again. So collab function just takes a batch, and then you apply operation on it and give it back to the data loader. Normally the collab function is empty. It just returns what the get item does, but sometimes you need to do a custom class function. So there is also like tutorials that explains whatever I said now, which is easy to follow. So yeah, next. Now, Hugging Face. So Hugging Face is basically GitHub for AI models. So you have a repository that have 100,000 of models up there. It's open source and anyone can contribute to it with datasets, models, and checkpoints. And it has a straightforward pipeline that makes loading, training, and using pretrained models a breeze. So Hugging Face also have a datasets module, but the difference between this one and the previous one, this one just contains the datasets and you can apply operations on it, but still it inherits from the PyTorch dataset module. So you can use this one directly, or you can create your custom dataset, and like you can have different ways to do the same thing a lot, usually. It has a evaluate modules. It has also the transformers module, of course, and the diffuser. We're gonna discuss these ones now. And finally is pushing to the hub and committing to the community. All right, for the datasets class or module, it contains large amounts of public datasets, and it continues to grow thanks to the community. We'll keep pushing new datasets every day. Allow easy and optimized processing of the data, pre-processing of the datasets. So you can do everything outside you. So yeah, like basic functions, you can always do them directly do them outside without relying on creating your own custom dataset, which is nice. Sometimes if your pre-processing is easy. So it's very simple to use. Just upload the datasets, the load datasets from your datasets, and then you specify the name of your dataset. For example, IMDb and whatsoever. You can find the datasets on the hub. Whatever dataset you want to use, you will find it. Just search for it. And here I was saying you can do simple operations on the dataset. Just define a function, and you want your maximum text to be 50, and you can just use the dataset, the one you just loaded with filter, and apply a function you want. There are also dataset.map, and there's several things you can do with the datasets. Here's another example that uses dataset.map. Which like I want to add padding to all my datasets. Instead of doing the stuff I was talking about, like custom dataset, call out function, and so on, here you can just do it in one line of code. Just define your tokenizer and dataset.map. Yep, you have everything done. So it's pretty convenient if your high-level stuff are easy to do. But if you're creating a dataset from scratch, you need to use the PyTorch one because it's allow more control over what you can do. All right, next is the evaluation. So Hugging Face also provides access to a wide range of evaluation tools. And it can also be used for visualizations, but I don't really recommend it much. So everything is under the evaluate class. So you'll have a lot of metrics. You can just evaluate the load and your metric you want. There's accuracy, precision, recall, F1, there is rouge, there is blue, there is cider, there's almost most of the evaluations that you would need. And it's very easy to use. You just have your normal training loop. And when you have your predictions, you add, like you use the object you just created from the evaluation, and you add batch by batch. You give it the predictions you have now and the targets that should have done, and you keep adding the batches. And after you finish, you just call accuracy.compute. Another thing, you can just have a list that you can append everything to it and put the list eventually. This also works, but I think this is easier to use. Here's also a quick guide tutorial about what kind of evaluation codes is there and how to use them. Hugging Face tutorials are super easy to follow, honestly. Like it's quite intuitive and have really decent examples. All right, next. Now for the transformers library. So the transformers library allow access to a massive number of models based on the transformer architectures and checkpoints. Some of them are official, released by the creators of the model, and some of them like just community contributed. So it focuses on tasks related to text classifications, question answering, image captioning, and text generation. And this is how you can use the transformers library. So transformers have submodules, so every family of models have a submodule. For example, you have BERT tokenizer, you have BERT for sequence classification. So you have some for BERT, some for GBT2, some for T5, and so on. So how do you know which one to load? You check the documentations. We will quickly have a quick overview of the documentation in a few minutes. So you load the correct family, the correct submodule you want from transformers. And you just simply just use the submodule from pre-trained, you get the pre-trained version, and load its tokenizer and also load its model. It's very easy to know how to load them. I will just show you. It's super simple. You don't have to memorize anything. Here we create a data set just as we just did and do tokenization as we did and so on. So for training with transformers, you have two options: either to use the normal PyTorch loop, where you define everything yourself, or just use trainer. So in transformers, there's something called trainer, which just can take care of everything for you, just giving it the training arguments, what arguments you want to use, and you just give it the model and the arguments and the data sets, and it's just do everything for you. It chooses like it does a backaggregation, it computes the loss, it gives you back the loss, and so on. It just do the entire for loop for you, like the basic for loop for you. I don't like it, to be honest, because I like to play with my for loop a little bit, so I usually use the normal for loop, but it's preferences. Here I want to show like how do you do a custom model. So for example, here I loaded BERT and I want to use BERT for classification. So I create a class that inherits an input module, as we have shown in the simple model that we showed before. And the init, I will just get our BERT model from the hub, and I want to add a linear classifier to it. So I just want to know what is the hidden output size of the BERT, and then I want to have a simple classifier on top of it. So it's very simple. I just get the output of the BERT. I call BERT as I would call it normally. And I just add the linear layer I want. So when you call BERT like this, the outputs, you will have several things. You have the input IDs, the output IDs, and you have the logits. So that's why you use the first one, which is the logits. And here we are just adding a dropout to avoid overfitting, and just the classifier just created over there, we give it the output of our BERT, and we return the logits. So they're very simple to use, like a pre-trained model. You just consider it a layer and then continue the model as you want. You can also use some specific layers in it, because transformers is modular, so everything is in module, so you can just pick part of it. You can print the model and pick specific parts of it. And here I want to show a generation example. So I'm using GPT-2. So as I was saying, everything have a submodule. For GPT-2 is called GPT tokenizer instead of BERT tokenizer, and it's called GPT LM head model. I'm loading both from the hub, adding it to a GPU, and to give an input, you need to encode it first with the tokenizer. So once upon a time, I wanted to continue a story. So I just use the model to generate. So model to generate is what you use to give an output for your autoregressive model. You give it the input IDs and the maximum length you want, and then it will give you tokens. You just use tokenizer to decode the tokens into actual words. It's very simple to use generate also, generation models. And yeah. All right, so next. So after we talked about transformers, we have diffusers that we discussed. So diffuser is similar to transformers, but it contains publicly released diffusion models. And it focuses only on image generation tasks, unlike transformers, which more towards text generation. So similar to transformers that have submodules, diffuser also have submodules. The main ones are just the diffusion pipeline and the scheduler, as it was discussed in the presentation before me. So we simply like, we're gonna have a diffuser for CFR10. So we just load a data set that called CFR10, which have like small images. And we wrote our model from the hub, as we saw with the transformer, just from pre-trained and the name of the model. And we load a scheduler and decide how many denoising steps we want. And you have an optimizer, and you create your data loader as we showed before. And this is how you can use a for loop instead of trainer. It's just a simple for loop. And you take your images and you have a random time step from the scheduler, pass it the image, and then you have your loss. It's just like very simple, like exactly how you saw the pipeline going in the presentation. This is exactly what you do in the code. You just get a random time step, you give the model with the time step, you get a loss, you do loss backward. And everything is predefined in the pipeline, so you don't have to define your loss function or anything. All right. So let us have a quick look on how the documentation looks like. So here is so here's the BERT documentation. So this is the BERT I was using. You can look for the documentation. It shows you everything in the function you're using. It shows you what config you can give it to your models. Like you can change the vocab size, hidden sizes, fully connected layers, number of hidden layers, and so on. And it shows you like sample codes of like how to do each step. So instead of looking at like the default model, you can change the configurations and so on. So this is the documentation of each model. You can find it for all models like GPT. You can find one for GPT Neo or GPT-2 and so on. And there's something called model card, which shows you how to use this model. So here's like gives you an example of how to use the model and also how to load the model. So you just click use this model, transformers, and it gives you the two-line code I just showed you. It's very straightforward. Also the same for the diffusers. It has the same idea. It's like it has a documentation that shows you what you can do with it, and different models with different model cards that shows you how to use it and how to get the outputs and so on. So the documentations are very essential to do. You can look at model cards here, and the documentation you can access it from the documentations. Like just Google like Hugging Face documentations and whatever model you want. All right. So now, right, I'm getting outside, right. So pushing to the hub. So after you trained your model, you can contribute it to amazing community we have, which just these lines of code. You just get a token. So when you create a Hugging Face account, you have in your profile a token. You just paste it here. You log in, and then you push your model to the hub. Like model to push to hub, and then the name of your username and where you want this model to be called. It's like similar to GitHub. You can also use the GitHub commands, but like I think this is easier. And there's also a tutorial how to upload your models, and it's straightforward. All right, so now we finished with deep learning. These are quite essential tools you can use. You will need them while working. And also this link have a very nice something called the missing semester. It was created by MIT like a few years ago. It covers a lot of stuff that you will not be taught in the university or school or whatsoever. Like how to use a debugger, how to use like version control and so on. It has really nice stuff. You can have a look at it. All right, so we start with Python debugger. It's built in Python. If you download Python, you have a debugger directly. You don't need to download it or install it. It's better than using print. So debugging is want to know what's wrong with your model. So one way you can do is just print in every single step in your code. You just have a print statement to see if you're going right or wrong. It's not that good. So cool kids don't use print, they use a debugger. And it works everywhere. Like you can use it in command line, you can use it in IDE, you can use it everywhere. So it's quite important tool. So the core function you can use with debugger is breakpoint. This is where you put it in your code, where you want your code to stop, and you start seeing what's wrong with your code or the outputs and so on. So the most important debugger commands are continue. It will run your code until the next breakpoint. Next, we'll run the next line. Interact. If you want to run multiple lines in your debugger, you just click interact, and you can, like for example, run a for loop. Because without it, you just have to run line by line. You can't copy a chunk of code and paste it, for example. And finally, break is the exit execution. Here's the documentation, but it's super annoying to follow, to be honest. So I don't think you will need anything more than these commands. So the second thing I want to talk about is IDEs. So integrated development environment. So before IDEs, people used to use Vim, which is the default text editor in Ubuntu, and life was not easy with Vim. Like it's not a nice thing to use. It's like using docs for programming. It was really nice, sad, but it looks cool. Like when you see someone working on Vim, it looks very cool. It feels like they know what you're doing. So IDEs makes life easier. It has colors, it has syntax check, and it have autocomplete. It's a really nice thing to have. And it have interactive debugging. So instead of just running line by line, you can have an interactive debugging with seeing your variables and everything while still in your debugging session. Because In the normal Python debugger, you can't see the variables, you have to print them. And finally, it's easy to integrate with other tools. For example, you can use GitHub easily with IDEs. You can Copilot, which makes coding like what takes an hour takes 30 minutes. It's quite nice. So examples of IDEs, Visual Studio Code and PyCharm. Here's a link for both of them. It's personal preference what you want, but both are equally good. The second thing I want to cover is Anaconda. So it's a package and environment manager. So some codes requires specific packages and libraries. So this helps having different environments for each code you have. And it takes care of dependencies. So some libraries require a specific version of other libraries. So Anaconda takes care of this to just like matches every library install with other dependencies you have, which is super cool. It's slightly slower than Python Wheels, but given the previous two benefits, it like the bros out carries the cons. It's not that bad, like, but Python Wheels are slightly faster, honestly. So next is weights and biases. So it's a fancy logging tool. You can keep track of your logs of different experiments in it. It's web-based. You need to create an account for it. You can monitor your model across different experiments and creating figures for different parameters. So what's cool about it, you can push different models you have, and then you compare all your models. For example, you want to see which learning rate is the best for your model. So you run different models with learning rate, and you upload the results to weights and biases. You can just visualize the difference between different experiments. And it's very easy to add to your code. It's just a few lines. You just use OS.environment and give it the weights and biases key you have. You get it from your account that you create on weights and biases. You give it a config, which is like just, this is the config is just literally for you. It's just a dictionary. You just mention the parameters you were using for this experiment, so you can see it later. And you just say with weight and biases that you just import WANDB, and then with WANDB.init, and then the name of your project and your config file. This is optional. This is to watch your model parameters and everything. It's not that important. This is the important part, is to log the training loss you have, the validation loss, the accuracy, and so on. So you can have some like useful statistics to compare to your model. All right, the tutorial is super nice, and this is some example for how it looks. So you can see, you can compare two models and how they like fare in front of each other. You can see how your learning rate is going and so on. Super nice tool. It makes life easy to like see the best parameters you. All right, so finally, the last thing we have is GitHub. So GitHub is a version control, which is a fancy word of saying that it saves all the code changes you have. So you can have several different files from the same project. For example, I have a project that I wanted to change some specific functions in it, but I was afraid that it will break the code. So I will just have a version of this project without these functions and a version of this function. So that's what's version control called. You can just keep tracks whatever you're doing. You keep pushing your changes. It makes collaboration very easy. Someone else across the globe could be working on your code, and you just keep pushing to the GitHub and you see what changes you made and fix it together. It's super nice for collaboration. And it helps keeping track of experiments. So you can have different changes on your code one after another without losing your previous experiment. So the basic ones you would need is git init. Just start your GitHub repo inside your file. Git add is if you want to add all your files that you changed in your current project, just git add space dot. And if you want to use a specific name, you just say the file name, or if you don't want to add extra files, just want to add the changes to the files you already added before, you just use u. Git commit, if you want to commit to your current code, which is just saying like, all right, this is the changes I wanted to make, and this is what I did, and you put a message. So now you have committed the stuff locally in your temp file. So if you want to push them into the GitHub repo online, you use git push, which puts your changes online on the cloud. Now, whatever you can later pull it if you want. Oh yeah, and GitHub like requires you to create an account, of course. Git pull is getting the changes from the repository that you have online. For example, if you're collaborating with someone and he did some changes, you need to do git pull to get the changes back to your local machine. And git fetch also gets it's more general way of get pull. It fetches all the branches on the repository. So get pull like pulls a specific branch, and get fetch pulls everything. I didn't mention what is a branch. So I was mentioning like you have multiple versions of your code, right? So usually you put every version on, like every major change on a branch. So instead of just keep looking like, all right, so where did I have this function before? Ah, it's in this commit. No, you cannot just like have different branch for different experience you want to make sure on your model, and just load these branches one by one. You just don't need to go back and look at one of the branches, like when did you make this change? Because as I was saying, it just keeps tracks of every change you have. This is a very nice documentation over GitHub. You can see it to have more details. And sorry if I was very fast. I just wanted to cover as much things as I can. And yeah. Oh, I forgot to mention git checkout. It's used to change branches. All right. So I'm really sorry if I was fast, and I hope you guys like benefit from this. And if you have questions, please.
Thank you for your talk. So far, we don't have any questions, and we still have time. So if you want to elaborate on some of the topics that you have just covered, you can do so.
So I'm not sure what I can elaborate on, honestly. So
Okay.
if someone like have a specific question of something that I moved on fast would be nice, so they can point it so I can like elaborate more on it.
Just thanks for the very cool presentation in the chat. No real questions so far. Okay, we gave our participants some time to ask their questions, but there are no questions so far. Thank you once again for all your presentations. If you have anything else to say, now is the time to do so. Okay, no questions, no comments. Let's call it a day. Thank you once again, and we'll see each other at the first edition of the Artificial Intelligence Olympiad.